Thank you very much, Carol and Wojtek and other organizers for this wonderful conference. I'm really sorry that I couldn't make it to be in person there. So I'd like to start with my favorite Hadamard matrix, 1, 1, 1, minus 1, and with the portrait of most famous person in this area, perhaps, next to Hadamard, or maybe before Hadamard. And his wonderful life history, which is available in my tutor at the University of St. Andrews. So here is a very simple and elementary balancely splitted Sylvester Hadamard matrix order 4. So we just picked the first row as one part, and the next 3 rows as the next part. And this is what we call balancely split. If we multiply now H1 transpose to H1, we're going to get the matrix all 1. You notice that all the entries off diagonal are only 1. And if you do the same to the second part, H2 transpose H2, we get again all the off diagonals minus 1. Minus stands for minus 1. So this is actually true for any normalized Hadamard matrix. So every normalized Hadamard matrix is balancely splittable in this way. We get off diagonals always 1 if we really pick the first part, only the first row. Now, here is a balancely splittable Sylvester Hadamard matrix order 16. By the way, there is nothing special about Sylvester Hadamard matrices, but I'm just trying to repeat his name in this conference. Anyways, so this is split, as you can see, in 3 parts. This is first part, second part, third part. First part has 4 rows, second 6, and third 6. And I call this one balancely splitted because of the fact that if you pick now these 3 parts, and if you multiply H1 with its transpose from the left, we're going to get again, you can see off diagonal now are 2 entries, 4 and 0. And if you do the same type to H1 transpose from the left multiplied by H1 and H2, you can see that again, off diagonals are only 2 or minus 2. So perhaps, you know, this is the best we can really pick from Hadamard matrix, so-called balancely. So that's what I call this one, a balanced split of the Hadamard matrices. The work started about 3 or 4 years ago with Sho Suda, very talented young mathematician from Japan. And later on, my graduate student, Tom Pender, joined us. And this work is now a joint work with these 2 nice people. Okay, now what happens, you know, if you pick now the first part H0, add to the second part, and we do the same, you can see that again, we get off diagonals or plus minus 2, and the same if you do it with H2. So that's why I call H2 and H1 a twin, actually. So we have a twin split of the Hadamard matrix order 16. So let me make now a formal definition. A normalized Hadamard matrix H is balancely splittable if we can split it in 2 parts H1, H2, in such a way that multiplying H1 transpose H1, we get at most 2 off diagonal entries. And so we call this one a balancely splittable matrix order N, and H1, we assume that its dimension is L by N. Indeed, you know, we can write this H1 transpose H1 as L times identity matrix order N plus A times A plus B times matrices of order 1 minus A minus I. And you can see that the right-hand side really reflects something really like a strongly regular graph. My interest, and in this talk, will be actually where B is equal to minus A. Now, in this conference, there's been number of talks where people have talked about equiangular line set. And indeed, you know, we pick a set of lines in RL, lines of vectors. We call them equiangular if the absolute value of the inner product of these vectors stays constant A for every U of an L in L. And we take now a finite set of lines in Rn and let the line Li be spanned by the unit vectors Ui. And then we say that this set of lines have form an equiangular line set. And an old result of Delstratz and Hutals and Seidel in 1975 gives an upper bound for the number of lines, particularly in the case that M is less than 1 over alpha square. Alpha is between 0 and 1. And equiangular lines form of it's called to be tight if the lines span the space, and indeed, you know, if a frame is called flat if the entries are all the same, you know, of the same absolute value. Now, when we split Hadamard matrix, and indeed we can see here there are actually 4 splits. This is one. This is another one, this is another one, this is another one. And you can see that this balance split indeed gives us, I'm just picking one of them, the middle one. This is the lines in R6. And these lines actually form a set of equiangular lines. And these equiangular lines meet the Delstratz et al. Upper bound. So you cannot add any more to if you want to keep the preserve the property. So this is one reason why really we are interested in splitting Hadamard matrices. Quickly, you can get actually a nice set of lines. Every time you get a set of lines in here, we get in R6, we get also a set of lines in R10. And indeed, you know, every inner product here has its reverse, actually, it's negative in R10. So if you pick 2 lines in here, corresponding lines in R10 will be actually, the inner product will be negative to inner product here. Okay, so yeah, let me also talk about unbiased Hadamard matrices. Again, you know, there's been this concept has been mentioned in this wonderful conference. We call 2 Hadamard matrices unbiased if H times K transpose is the square root of N. N is the order of the matrices times the L, and L is another Hadamard matrix. And again, let's really look at this splitted, balancedly splitted Hadamard matrix. So we can see that the line sections being split. Now, what I'm going to do now, I'm going to negate the middle part. And if I negate the middle part, I get something like this. And then, surprisingly, when we look at these 2 matrices, the H, the previous one, and K here, now H and K are actually unbiased. So this is another reason why we're interested in these splitting. Indeed, people who are familiar with equiangular lines, they know that every time you have an optimal set of lines, then you actually have also nice codes, you know, Gray Rankin codes meeting the upper bound. And also, of course, you know, again, you know, symmetric, you get actually quasi-symmetric designs also from these. But we are skipping those 2 because, you know, cannot fit it, I cannot fit it in the stock. Okay, some properties of balancedly split the Hadamard matrices. Number 1, suppose that we have this H split it like this, H1, H2, H1 transpose H1 is L times IN plus AS, and S is actually an n by n 0, 1, -1 matrix. Then the following are equivalent. if we multiply H1 transpose H1 minus H2 transpose H2, this is exactly what I did with the previous one, and divide by 1 over 2 times A. A is of course this is the A. We're going to get a Hadamard matrix, and this Hadamard matrix and the original Hadamard matrix is going to be with these parameters. So the N must be a perfect square, and also this matrix K with the matrix H, these two are unbiased. Okay, so there are Hadamard matrices which are not balancedly splittable. So let's really see what we can say about this. If there is no balancedly splittable Hadamard matrix with the parameters N, L, A, if L plus A is not 0 mod 4. So this is a counting argument. It's a little tricky counting argument, but then this immediately implies that there is no balancedly splittable Hadamard matrix of order 4n square n, an odd integer. So for example, we don't have one of order 36. And indeed, for order 36, I don't really think there's any flat ETF known, equiangular EFT known. There is one known optimal set of equiangular lines, but they are not really, the coordinates are not flat. Okay, now let me summarize, what we know about Hadamard matrices. Number one, there is a balancedly splittable Hadamard matrix order 4n squared for any n, an order of a Hadamard matrix. So, for example, if n is 4, we have one of order 64. If n is 12, we have one of order 576. And here I have n equal 12, so it is 4 times 3, leading to an order 576, which is 64 times 3 squared. There is a twin set of flat ETF meeting del Sart et al. Bound in R2 to the n squared minus n for each n an order of Hadamard matrix. And no Hadamard matrix of order 4n squared n odd is balancedly splittable. And the first question is, of course, as you can see that, the order 64 of this R3, we know that it exists, but not really order 16 times 3 squared, namely 144. So we really don't know if there is a balancedly split for Hadamard matrix of order 144. This is one open question. We know that there is actually a complete set of ETF in R12, but we don't know if any balancedly split Hadamard matrix order 144 exists. Now, there is a balancedly splittable quaternary Hadamard matrix for the 16n square. Quaternary means, the entries of the matrix are fourth root of unity plus minus 1 plus minus I. And of course, n must be here. There is assuming that there is a quaternary Hadamard matrix of order 2n. And in case of n equal to 3, of course, tells us that there is one of order 144. So although we don't know if there's a real one balancedly splittable, but we know that there is a quaternary one balancedly splittable. And finally, if we know that there is a balancedly splittable Butson Hadamard matrix, Ronan talked about Butson Hadamard matrix, and in the talk before my talk, again, Butson Hadamard matrices came about. We know that Butson Hadamard matrices of order 4n squared n odd are splittable, actually, balancedly splittable. So for order 36, then we have a flat ETF. And of course, as I said, case of n equal to 3 leading to order 36. Okay, now I'm going to give a proof, a construction, a quick construction. And for that, we actually observed that we can even extend, the concept of balanced splittable Hadamard matrices to a wider class, namely orthogonal designs. And orthogonal design, the entries now are variables, including 0, and the rows must be orthogonal. So, and indeed, balancedly splittable, if we can write it, something similar to what we had for Hadamard matrices, except that sigma is actually something like this. Sigma is sum of the square of i's x variables times the number of times the variable is repeated. So let me give an example here. And again, this is order 16, and again, this is splitted, balancedly splitted. What it means, it means, if you look now to the blue section of this orthogonal design. First of all, this is an orthogonal design, namely every 2 rows are orthogonal, considering A and B as commuting variables, right? Now, if you multiply every 2 rows, you're going to get, as I'm going to show you in the next slide, you're going to say the constant a squared plus b squared minus a squared minus b squared. Now, this is one split here, and indeed, this is also balancedly splittable if you pick this part. However, when you look to the horizontal ones, they are not balancedly splittable in terms of orthogonal design, but in terms of Hadamard matrices, they are. If you replace A and B with 1 and 1, then you get an Hadamard matrix. And of course, orthogonal designs are extension of Hadamard matrices, right? You will get actually the same thing that I have shown you a number of times so far. So this is an example of balancedly splittable orthogonal design of order 16. And indeed, if you multiply B by B transpose, we're going to get off diagonal either A squared plus B squared, or we get minus A squared plus B squared. And indeed, the same is true for the third part, namely for the part C, as was shown on the graph. Now, I'm going to give you a quick construction of these matrices, and I will be quick because I know it's been a long day, and there's been wonderful talk so far, and I know you're tired, and I have to say that I am also a little tired because I've been staying awake, and so I made my own job easy, and so I'm really going to go through this by examples. So here, I'm starting with my favorite orthogonal design, order 2, A, B, B minus A, and I make 2 auxiliary matrices from this. Namely, I multiply the row AB from the left by matrix 1, 1, vector 1, 1. I'm going to get this matrix. And I'm going to pick the second row and multiply from the left by vector of vertical vector 1 minus 1. I'm going to get this one. You can see that these 2 matrices of rank 1, right? So now, what's really good about these 2 matrices, they're orthogonal to each other. If you multiply this to transpose of this, they're going to be orthogonal. Indeed, now think of this really as in a larger stage. Imagine, you have a larger orthogonal design. Imagine you have a Batson Hadamard matrix over, let's say, roots of third root of unity. Anything, the orthogonality on the large matrix can be carried over to these auxiliary matrices. I have used this, for many years, and indeed, it has made my job much easier. Anyways, so the construction goes step by step. Step 1, form the block-Barker sequence. Now I talk about block-Barker sequence. I take C0 and C1 in row. This is a sequence consisting of first matrix C0, I showed you in the previous slide, and C1. It is Barker. It's a block Barker. It means if you shift to C0 and to C1, the 2 are orthogonal to each other. Namely, the autocorrelation is going to be 0, blockwise. So the block autocorrelation is 0. So we know that every time you have a Barker sequence, you can make always a Golay sequence. So then in the second stage, we form the block Golay sequence. Namely, I put a C, I put a C1 on the right and the minus C1 repeated. Now, this is a Golay pair with sum of autocorrelation 0. So if you find autocorrelation in the 2 sequences, in blockwise, you're going to get 0. And form two block circular matrices. I now form two block circular matrices from these. Namely, I just pick, the first row of my first matrix, block circular matrix to be C0, C1, C1. And the second one, C0, C1 minus C1. And these two actually now are block complementary pairs. Namely, the long rows are blockwise orthogonal to each other. And then form the matrices A equal to B circulant and B circulant. And here we get the corresponding matrix. So this is the, as you can see, as 12 by 12 matrix, and consisting of A, B, C, D. Now what happens in here, you can see that here, this is C0, and this is C1, and this is C1. This is C0, C1 minus C1, right? So, and then I'm circulating these blocks, right? So what happens in here, you can see that when we multiply theta by its transpose, we're going to get, of course, all zeros, except for some places. And the reason is because we are really handling blocks. We are not really handling simple rows, right? So for the blocks, we have this one. Now, what I'm now trying to do now, while I'm going to extend this matrix, this matrix to from the left side, and I try to really make the rows orthogonal to each other, then you can see that I have to add, actually, you can see this is my matrix, my matrix is there. So I have really 9 pieces to fill now. I have 9 pieces, already 4 pieces are filled. So I have to fill this part. I have to fill this part, this part, this part, and this part. And this is really something that we've been trying for the first time, really trying to make, these matrices from small pieces putting together, and using, of course, the properties that we know very well, about how the sequences work in action. Okay, so and I'm going to really go a little quick over this one because it's becoming really a little technical in here. So I'm going to find matrices E. Fortunately, E with minus E works, and then F, I can actually put minus F there, it works for this particular construction, and a matrix G in there, right? Now, I'm trying to make, these long rows orthogonal, and something really happens here, I have to say unexpected, namely the, I went too fast, okay, namely these portions of the matrix going to be balanced. While really we're really filling up these, we are trying to make these balanced, and it is possible. And I have to say that luck, we had a little bit of luck with us actually in doing this, because well, I don't need really to explain, Anyways, so now I'm going to just fill up, E and minus E, and we can see that this is E, this is minus E, this is F, and this is minus F, and we fill up the part in here. And indeed, this is now giving us a splitted orthogonal design, order 16, in 2 variables. Okay. The essential part that we should remember here is orthogonality of the original matrix. If the original matrix is orthogonal, then those orthogonal matrices, auxiliary matrices, are possible to be constructed. Then Barker sequence is there. Of course, you're going to have more auxiliary matrices, and Barker sequences, you just put, orthogonal matrices beside each other. Again, you get a Barker sequence, then you complement it to Golay sequences, Golay pairs, and then, of course, you continue with the construction. And that's how much I want to really talk about construction, and the explanation here is from an if you start with an orthogonal design of order 4 in 4 variables 1, 1, 1, you're going to get balanced splitted orthogonal design of order 64 in 4 variables, 16, 16, 16, 16. Each variable is repeated 16 times. We cannot do better than this. Indeed, for the real case, we cannot do better than this. Here it is, this is part of balanced splitted orthogonal design of order 64 in 4 variables. This is the part of it. I couldn't fit it in one page. And this is the second part. And let me give you another example. If we have a Butson, let's say a Hadamard matrix of order 3 on the 3rd root of unity, we can actually construct a Butson splitted, balanced splitted Butson Hadamard matrix of order 36 in the 6th root of unity. Obviously, we have to really add minuses. So from 3rd root, we go to 6th root, actually. We know that there is no balancedly split Hadamard matrix order 4n squared in an odd integer. But of course, there is a balancedly splittable Butson Hadamard matrix of order 4n squared in odd for which n must be order of a Butson Hadamard matrix order n. Well, again, the construction is just the same construction. Wonderfully works for any things, orthogonal matrices like Butson matrices, and I'll give you next, a quaternic orthogonal design. Okay, so here we go. We start with the Butson Hadamard matrix for this over the 6th root of unity. Actually, this is on the 3rd root of unity. And this is as was previously shown, this is the log of the actual matrix. And the corresponding Butson Hadamard matrix order 36 on the 6th root of unity is right here. And again, we have here, is one part splitted, and this is to twin part splitted. And now I'm going to give you an example of quaternion OD211. And you can see that from this one, order 2 in AB, and the elements of quaternions, and AB must be real variables. And then we have one of order 16 in quaternion elements. Again, as I said, every time you have variables, only the construction that we have given you gives you really vertical balance split, and the horizontal ones, if you replace the variables with 1, then you get actually also the horizontal ones are also balancedly split. Okay, so this is the main theorem. So you're starting with an OD of order n of type S1, S2, Sk, namely, so we have Sk variables, commuting variables. First one, x1 is repeated S1 time, x2 is repeated S2 time, and Sk is repeated Xk is repeated Xk time. Then we can actually construct an balancedly splittable orthogonal design of order 16 n squared in 16 in K variables. And of course, you can detect an error here. Each one of the variables must be multiplied by 16 in order to really get this one correct. And these leads to ETF meeting their sort of upper bound and unbiased orthogonal designs with these parameters. Again, errors can be spotted here. And I wish now to offer a huge thank you to the organizers and to the audiences. And thank you very much for your attention. And that is the end of my talk. And I have met my limit on time, maybe even 5 minutes earlier. Now, ready for questions if there is any.